Now let's jump to the Kalman filter extension, so-called extended Kalman filter. And today we're going to finish that as well, hopefully. I think now I don't need to cover extended Kalman filter even. You don't have a lecture note? Okay then. No online? I think definitely we'll send it to the WeChat. Extended Kalman filter is maybe used more widely in applications because in reality a lot of physical systems are not linear, okay, are not linear. But we don't need to spend as much time as we did for the Kalman filter because the principles are there. So let's state our principle first. Let's recall our principle is just whatever you want to estimate as a hidden variable based on some measurement, you need to find the conditional expectation. That's according to minimum mean squared estimation rule. Okay? For extended Kalman filter, or for nonlinear case, nonlinear Gaussian case, nonlinear non-Gaussian case, we still need to do this. Are you with me? There's nothing changed. The principle doesn't change. So we spend a lot of time to cover the probability and the minimum mean square estimation theory. I think all of this carry exactly over to here. Okay. And in essence, Kalman filter is just a recursive way to compute conditional expectation for linear Gaussian system, for which we have analytical formulas we just derived. Everything is accurate and exact. For nonlinear system, okay, let's look at this. Suppose we have a nonlinear system. It's not linear Gaussian anymore. So the state update equation is this is general nonlinear system corrupted by noise. Let's assume the noise are still Gaussian. It doesn't matter anymore, right? But let's assume it's still Gaussian with measurement noise covariance RK and process covariance QK. And the notation are pretty much the same. Okay. Now I'm going to ask you, in general, xk plus 1 is random, but it's no longer Gaussian. Okay, it's no longer Gaussian. We cannot use the linear Gaussian formula anymore. What we should do? Huh? It's not Gaussian. We approximate it as a Gaussian. It's just like linearization. It's not linear, but let's linearize it and approximate the dynamics as a linear dynamics. Okay, so you have seen a lot of examples. For example, not only extended Kalman filter, there are also, I think, ensemble Kalman filter, unscented. I don't know how to unscented Kalman filter. I'm not sure whether you heard about this or not. All of them are the same. In principle, they are trying to approximate as a Gaussian, but there's just different ways to approximate that. Okay? I think a little bit jump from this is so-called particle filter. Have you heard about this? What particle filter do? Using particle to approximate as a Gaussian? No, it's more general than Gaussian. It's particle to approximate the conditional density. Gaussian, if you know mean and covariance, the density function are fixed. Okay, but for other distribution, the density function is kind of very complicated, right? But I can use particles to approximate that density function. And then I can do either expectation or the maximum likelihood, either way is fine, to find the best estimate of my hidden variable. Okay, so all of them are related, and I think you have the foundation to truly understand all of them It's just different. They differ by their particular techniques to find the approximation. Okay, let's have a quick look of extended Kalman filter. By fundamental theorem of estimation. So yeah, what is the fundamental theorem of estimation? Read the formula. Okay, is this true under Gaussian assumption or not? True under Gaussian assumption. If it is not Gaussian, it's also true?
Yeah. Yes, it's been proved.
It's been proved in my lecture note, although we didn't go over them in class. Whatever distribution, I don't care. If one the minimum mean square estimate, this is the solution, conditional expectation. Of course, sometimes you don't agree on this mean squared error assumption or cost. You don't think that's a good call, you can use other things. Maximum likelihood, maximum map, maximum a posterior distribution estimate. But anyway, all that matters to compute this, we need what? Density, all right? Conditional density function. So it's xk given yk of xk given yk, for example. I need a density function before I don't dive into the detail of the density function because it's completely characterized by Gaussian. For Gaussian, it's completely characterized by mean and covariance. We only need to know these two things, right? But now, if it is not Gaussian, I need to know the entire distribution density function, right? So for extended Kalman filter, we're doing exactly the same thing. We just need to compute. Our goal is to compute this conditional expectation, okay? To compute this, we need this conditional density, okay? But now we are not living in the linear Gaussian case. It's no longer linear, it's nonlinear, so xk, especially xk given yk, is no longer Gaussian, okay? It may not be Gaussian. So extended Kalman filter try to approximate this as Gaussian and propagate it through linearized dynamics. How to approximate something as a Gaussian? What characterizes Gaussian, Suyan? What defines a Gaussian? What characterizes Gaussian? It's mean and covariance, okay? So it's a mean and covariance. It's a mu and a sigma, right? And this density is given. If you know these two, then if I draw one-dimensional case, it's like a bell-shaped thing, right? This is the mean, and somehow covariance determines how widely this is. Only these two parameters you can adjust. Okay, you don't have other freedom. But if something like this, let me ask Xiaohan, something like, suppose I have density function like this. This is too bad, all right? Maybe something like this. Do you think it's Gaussian? Looks not, right? How do I approximate as Gaussian? All I can do is move my distribution around and scale it by this density function. This guy, right? So maybe I will do like something like this, right? And try to adjust this standard deviation or covariance parameter to find the best fit. Okay. So our rule is that. So suppose. Let's say, let's do some notation. So this guy, this guy is not Gaussian. This guy called X is not Gaussian. okay? And I want to approximate this guy using the black one, which is x hat, approximate x, okay, as a Gaussian. So I would say this guy will be x hat, will have a mean and covariance. Let's both call them hat and hat. So extending common filter try to do this approximation, or it's very naturally. It's just these two things has to agree, right? So first of all, I would say we can do this by matching the two moments, or these are called moment, first and second called the moment, okay, of the matching the first two moments, okay? For example, I was a male hat. I want to design a Gaussian whose mean agrees with the random variable. Give me a random variable, although it's not Gaussian, I can compute its mean, okay? It's not a Gaussian, nicely looking Gaussian random variable, but I can still compute its mean. And also, sigma hat, I can compute its covariance. For arbitrary random vector or random variable, I can compute its covariance. And that is two agrees, then I don't care the rest. Okay? The approximation may be good or bad. Okay, for example, if I have a like this density function, then my approximation would be, I don't know, something like this. Okay, which may not be good enough, right? In this case, what would be a good approximation? You may have to use some particles. What does particle mean? It's like a histogram. You know histogram, 柱状图是吧? You generate a lot of distributions and using particles, the distribution of particles like a histogram to approximate its density function. That becomes particle filter. That's exactly what particle filter is doing. Now in this class, we still do Gaussian type approximation. That's where we start talking about extending common filter. Okay? So that's the key idea. The rest will be very simple. Let's say approximate the linear dynamics and linear dynamics. In this case, I can relate the previous step to the next step through the linear transformation. Let's see some details, okay? Notation are still the same. This guy is my best estimate of xk given time k, measurement up to time k, and xk given k, this is the prediction step. These are covariance, are defined exactly the same as common filter, but now they are, I would say, after the formula doesn't give me the exact solution to them now. I can only find approximate version of those variables. Okay, so I still break up the whole thing into two steps. This is the prediction. This is the measurement update. Let's look at the simple case, prediction. Prediction means now I have these two guys. I have the best estimate, which is expectation of xk given yk, and its covariance. I want to find what should be the next best estimate. All right. Let's quickly summarize the result. So for now, let's say our xk plus 1, by our model, what is it? It's fxk uk plus wk, or omega k. That's my true model, right? That's my true model, and you should be able to write down this rk, this rn times rm, because u input is rm, maps to rn. Okay, let's update my state to the next time. And I can because I have the formula for linear version of the system, right? If it's linear dynamics, I know exactly how to update the mean and covariance, right? If it's nonlinear, I can compute, but I don't want to compute. It takes a lot of effort if it's nonlinear. So let's linearize it. So how do we linearize? That's my lecture note 2, right? You should review that. I think most of you are okay with it based on the midterm result. And so I can approximate that, linearize it. Around where? It says linearize around the current best estimate and the current input. So now you assume your system operates at xk hat. I just linearize my dynamics around this best estimate point. Okay? So using Taylor expansion, that will be xk hat, we'll plug in, right? And the uk plus Jacobian, right? Partial f, partial xk, given xk equal to xk hat, and the uk equal to uk. It's a function of xk and the uk, right? You plug in these two. This will be a matrix, right? Times the deviation of xk minus your operating point, which is xk hat now, plus hot, high order terms. I don't care. As an engineer, that's our freedom to ignore everything. Say it again? UK is known. Yeah, of course. We can have that, but it doesn't matter. Let's have that. For simplicity, for completeness, we need that, okay? Partial f, partial u. Evaluate that xk hat, uk. Okay? This is our B matrix now. And the uk minus... No, I don't need that, sorry. I just treat it as no control input. Okay, everything is given because it's time varying. You can normalize, linearize with u as well, but you know, let's not do this, sorry. Yuntian, we don't have to do it. I only linearize by what? View it as a function of x. I don't care about u anymore. U is given, all right? That's high order terms. You will see that later. Okay, so now if that's the case, then I will say xk plus 1 is approximately fk, xk, plus what? F xk hat uk minus, let's call this guy, define this as capital Fk. It's a matrix. What's the dimension of it? What's the dimension of it? N by n. Right? I linearize with respect to x only. Okay? It's a n by n matrix, of course. So this will be our Fk. This is Fk as well, sorry. Minus xk hat. Xk hat. So that's the term, right? This is this term. And plus high order term, I don't care. And plus omega n, or omega k. Well, I didn't do anything. I just split these two terms. This just Fk times xk minus Fk times xk hat. And let's view this guy. That's my answer, okay? View this guy as my uk. Let's define this as tutor uk. First of all, I know everything here, right? At time k, I know sk hat, and I know uk, right? uk is my true input. And I can do linearization. I can also find fk, and I also know xk hat. So everything here is known, is as a number. Okay, I call this guy UK tilde because deterministic numbers or a vector doesn't matter for filtering or for Kalman filter. Okay, that's my update equation. This may be my A, and this is my some deterministic input. Okay, this is noise. What about x? So then I can sk plus 1 given k hat equals expectation of xk plus 1 given yk. That's my hope. I want to compute this, right? This will equal to, if I substitute this in, this is equal to fk xk plus uk tilde plus omega k given yk. So because I linearize it, now I can move things out. So this will be fk times what? Expectation of sk given yk. That's xk hat. And this is deterministic at time k, so this will be uk tilde. And the expectation of wk given yk is 0. Okay, so you find out this is nothing but fk xk hat plus this thing. Somehow I'm moving it back, sorry. I'm putting it back. I just plug in fk xk hat. You see something, this guy got cancelled. And this is nothing but xk hat uk. All I did, actually this step, prediction step, is nothing but plug in my best estimate of xk hat and my current input and then ignore noise. So that the prediction means basically the best prediction here is just ignoring the noise by assuming the noise is 0 and evolve your system deterministically. My question now, I don't know how much time I have. Okay, my question now is the following. So it looks we're doing something unnecessary, right? So let's say we want to find xk plus 1 given yk. Let's say without, let me do this, so-called without linearization. Let's say we don't do linearization, what will happen? This will be expectation of f xk uk given yk. Also w, but w will be 0 anyway, so this will be given yk, right? So it will be equal to expectation of f xk uk given yk. My question is this equal to, because u doesn't change, right? So is this equal to, does this equal to this k hat uk? Huh?
No.
No, why?
Because we ignore some file reference, then they will be equal for our.
I'm not sure whether, yeah, so that's the right direction. Let me write it more clear. Can I move this in? So that means because only randomness is here, right? This part is known, I don't care. The expectation of xk given yk and the uk, and this guy will be xk hat, right? If this is true, then I don't need to do linearize. I just plug in. So the question is that. So the answer to the question is, I don't have the answer for you. No, sorry. I have the answer, but I don't want to direct tell you, but I wanted to think about this case. Does expectation of, let's say, x squared equal to expectation of x squared?
No.
If it's nonlinear now, right? It's nonlinear. This is not true in general. right? So you can now move the expectation. This is what? This is a function of fx equal to what? X squared. So in this case, you can now move the expectation inside f because it's nonlinear. The only reason somehow you get this result is not because you can move the expectation in, it's because we do a linearized case, okay? If you assume a linearized model, then this is correct, okay? And once we get the linearized model, our linearization model is this part, okay? And we can directly compute update based on, so these are what we derived, right? This is our formula 1, this is 1. Okay. For the covariance case, we just use, because we have a linearized model now, right? And we will just do, you see where's the linearization step? We call it linear case. The predicted covariance is AK, PK, HK transpose times plus QK. That's the update for the covariance matrix for the prediction step. And here, we just replace AK with FK, where FK is the Jacobian. Any questions? For the prediction, what we derived so far is nothing essential, okay? So the prediction step, you should somehow understand it as the following. You just plug in your best estimate at current time into your state update equation. You got your best prediction of next time. The only thing we did is plug in the best xk hat to replace xk, and also assume zero noise for the process noise for the prediction. That somehow is optimal if the system is linear, and it's optimal if it's nonlinear. It's optimal if we assume we can use a linearized model. And the covariance step, the covariance is just this. Just replace FK, because you have a linearized model, you replace FK with AK with FK. The second part is the measurement update. This part will be even simpler. We spend a lot of time for covering measurement update for a Kalman filter, but if you understood that part already, then extend this to extended Kalman filter will be fairly simple. For this step, we have xk plus 1 given k hat, and the pk plus 1 given k. And we do the update. Before we update, that relies on linear model, right? It's a linear measurement model. So here, the only thing that matters is that now our measurement equation is, let's say k plus 1 is no longer a linear function of state. It's nonlinear, right? It's uk plus 1 plus vk plus 1. And we do linearization with respect to x. We only care about x. So this will be where to linearize it. Well, some people use different things now, okay? So let's do, so the best estimate now is here. Because we haven't do the update yet. The best guess we can have for my state is k plus 1 given k, and uk plus 1. Here will be my linearization step, okay? And the plus Jacobian, right? Partial h, partial x. This means with respect to x. I don't want to write down all the sub-indexes here. So that will be, I evaluate at x hat, k plus 1 given k, and uk plus 1. This will be a matrix, right? Times xk plus 1 minus xk plus 1 given k hat. The deviation from your linearization point, plus high order terms. again, we define this guy as defined as what? HK plus 1. Overall, I will have what? Approximate. This guy will be. Let's call this HK plus 1. So HK plus 1 times XK plus 1. It's the same thing, by the way. So plus H XK plus 1 given K and the UK plus 1. Okay, minus HK plus 1 times this guy, right? XK plus 1 hat. Okay, plus, sorry, here there is a VK plus 1 as well, right? So VK plus 1 plus high order terms. That's my regrouping of the terms. Are you with me still? So now what we can do is the pattern matching, right? So let's C equal to HK plus 1. That's our C now, right? This is our C. Okay? And this will be our another so this part is some constant, right? Let's call this part, match over formula here is that some deterministic part, okay? I will call it D, small d is fine, right? So at this time, everything is known. Okay, let's call it dk plus 1. Some deterministic number here. And that's equal to this. And let's plug in to the formula, to the linear case. With let's say d times uk plus 1, that deterministic constant equal to our small dk plus 1. All right. So because measurement update only involves the measurement equation. It does not involve anything else. Okay. So by doing that, you can find the formula, which is, I think it's, where is it? Oh, let me copy this for you, okay? You can try to think about it later. So the best update is as k hat plus 1 given k hat plus k plus 1. The measurement plus surprise. Now the surprise, you can derive this, okay? The surprise becomes xk plus 1 hat given k, and this is uk plus 1. This is without noise, your best guess. This is what you see. This will be the new surprise. You can derive this by the previous steps. And what is kk plus 1 equals to pk plus 1 given k, that's we know before we enter in this step. Plus what? No, not plus, times c, right? C transpose, which is hk plus 1 transpose times hk. Just replace ck, c with h. And pk plus 1 given k, hk plus 1 transpose plus rk plus 1 inverse. Done. Not yet. One more thing. Ki minus kk plus 1, hk plus 1, pk plus 1 given k. All right, that's our extended Kalman future state update, measurement update equation. I'm going to post this online. I will give you examples. The codes are no longer 5 lines, just 7 lines or 8, if you know what's going on. All right, I'm going to show you two examples next time. One is robot localization for extended Kalman filter. Another one is joint state estimation and parameter, okay?